this is Mike from Fair Repair again, and today we want to talk about something special. We want to talk about the USB-C power delivery system, or in other words, why does it appear so complicated compared to the classical DC-in circuit with a hybrid power boost design? Because I realized it will be more and more a thing on modern devices like this Lenovo Thinkpad X1 Carbon generation 6. We have this circuit here also, a PD delivery circuit via USB-C. And yeah, I've seen many technicians get confused about this one, because before you had to deal with the classical design, you have to deal with two DC-in MOSFETs, and that's all. That's everything. And here we have the USB-C port with the different lines. We have maybe a Thunderbolt controller. We have some protection things. We have the PD controller, of course. We have additional the charging controller, of course. And maybe we have even something like a selector circuit, because the device might be not only powered via USB-C but also has a classical DC-in jack, or maybe a port replicator underneath. So yes, this can appear really complicated if you're not used to this type of circuits. For me it was, and it still somehow is the same, but well, let's try to dig through that as basic as possible. So yeah, we have this board and it has two USB-C ports. Here's one and here's another one. And of course it has a USB-C charger. And in my opinion it was a really bad idea to introduce them, because see yourself, this does not look like a strong and powerful DC-in plug. This looks like kindergarten. Yeah? Okay. However, many countries and also the European Union decided to introduce this, and even to persist that many manufacturers have to build these ports into their devices. Yeah, now we have this, and yeah, it is suitable for most of the devices except the most powerful. A high-end gaming laptop cannot be powered with this USB-C plug. This is impossible. So yeah, but for a ThinkPad like this, of course it is enough. And yeah, but now we have to deal with a few things here, because this charger has to talk with the motherboard before it really starts to work. Let's give an example. This is a random Apple MagSafe charger with USB-C, and if you take a closer look to this charger, you will notice here, it is not only rated for 20 volts, but it is also rated for 5 volts, 9 volts and 15 volts. So yeah, it can output 4 different voltages. But from where should the charger know what it has to supply? Yeah, it has to talk with the board for that. It's the same with this Lenovo charger. It is rated for 4 different voltages. So when I plug the charger, when it talks to the motherboard, and the motherboard will request the voltage it wants to work with, which is in this case 20 volts. So let's see how it works with this Lenovo ThinkPad here. Everything starts, of course, with the USB-C port. This here is the schematics of a typical USB-C port. And in my opinion, if you deal with a no power issue, then just ignore every pin of this USB-C port except the CC lines here and here and the VBus lines here. VBus, 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 VBus. So we have summarized 4 VBus pins and 2 CC pins. Yeah? And everything starts with these CC pins. Let's follow them. This CC line here goes to a line called TBTA CC2 connector. Let's see where it moves to. To this interesting component here. It gets power. I can already tell this power will be delivered from the PD controller. And yeah, it has a few pins for the CC lines, also something else, but just again, ignore that. Concentrate on the CC lines. The CC lines connect here, and it seems like they will just route it through this IC and moves elsewhere. And indeed, the component we have looked at right now is just a port protector. It protects the CC lines from a short between the VBus lines and the CC lines. And if this happens, when this IC will just fail, maybe it will get hot or something like that, and the charger cannot talk with the USB-C PD controller anymore. In this case, the charger will stay just at 5 volts, caused by the missing communication. So the charger will stay at 5 volts and that's it. However, if everything is fine, this line becomes TBTA underscore CC1 and reaches our PD controller here. It's a big PD controller. Here it is called SN something, but at the board itself it is a TPS 65988CE. So that's our PD controller actually. And yeah, now the charger can complete the handshake with the motherboard, the PD controller, and in this moment the charger starts supplying 20 volts at the USB-C port. Here, at the VBus lines. It isn't important which line exactly, because these 4 are all tied together. So these 4 VBus pins are tied together and becomes TBTA underscore VBus 20 underscore con. Yeah? And from here the journey of the 20 volts begins. And now we are looking at something similar like before. Something which protects the system from a fault, because the 20 volts from the USB-C connector are going straight here to this IC, and only if this IC decides everything is okay, then it will go forward and becomes TBTA VBus 20. It is actually this IC here. Over voltage protection load switch. So if it detects some kind of over voltage, when it just shuts down the system and the 20 volt cannot pass this part. Typical behavior could be here also, it might be get hot as hell, something like that. However, if everything is fine, the 20 volts can pass this component and becomes TBTA VBus 20. And then this 20 volts will reach the PD controller again, our TPS 65988CE. The PD controller is already powered even before the charger did the handshake. So even at the 5 volt state, the PD controller is already powered through this line here and starts the VCC free LDO PD. Low dropout regulator. And here again, it does many things, the PD controller, but let's stay basic as possible here. The only thing which is important for no power fault is our VBus lines here, the CC lines here, and maybe the VCC 3 LDO PD. And these voltages here, VCC 5M, VCC 3M, are supposed to come up later. These are always voltages which only comes up when the voltage has already passed the charging circuit. And from here the TBT A underline VBus 20 power rail reaches finally these MOSFETs here, PQ1 and PQ2, or for the other port, for the other USB-C port, it will be PQ3 and PQ4. And if we plug the charger in the TBT-A USB-C port, and if everything is fine, the gates will be supplied with 1.8 volts in our case. So this P-channel MOSFETs can open and let the current flow to the next direction. On the other side, for the second port, the MOSFETs gates will be supplied with 20 volts, so they cannot open anymore. So well, the charging voltage, the 20 volts, will pass this fuse here and also these two MOSFETs here, and also here's some kind of inductor, and then it will become VINT20_in and finally reaches our charging circuit, our BQ chip. It is in our case a BQ25700A controller, which is actually a so-called buck boost converter. So the 20 volts comes here to this MOSFET, and now I'm not sure even myself if I explain it properly, but from what I did understand, this first dual MOSFET is supposed to convert the 20 volts into 10 volts, because on the other side, at drain 1 of the second dual MOSFET, we have the VSys 15, which is actually 10 volts without battery connected. And from here we can troubleshoot as before, 3 volts LDO, always voltages, 3 volt, 5 volts, and so on. So this was the theory. Now, let's follow the path under the microscope with the ICs I've introduced before. So this is our USB-C port. Let's plug the charger. So, and from here the journey begins. It talks via the CC lines. This is our USB-C port protector from before. Here, the CC lines, you see 1.6 volts, and the other one probably has no voltage. Yes, only one CC line will be triggered. So here we have 1.65 volts as in, and it more or less goes straight through this IC on the other side. And now here we have the same 1.6 volts. Yeah? And from here we will move straight to the PD controller. So here's our PD controller, and responsible for our CC lines are actually pin 19 and 21. So pin 19 is here, and here we have the exact 1.65 volts like before. And here's the second CC line without voltage. Okay? So, and now our PD controller will talk to the charger and tell him I need 20 volts, And when the journey of the 20 volts begin, again from the USB-C port, at this moment the 20 volts are requested and the voltage of the charger raises from 5 volts to 20 volts. Let's check here, for example. We have 20 volts. And from here it will pass our over voltage protection load switch. Here is the input, 20 volts. And if we follow the line here, we'll come to this fuse here. Here, 20 volts at the fuse, which means the voltage has successfully passed the overload switch. Now we are already in the direction of the two MOSFETs we have talked about before. Also the voltage passes the PD controller itself at pin 11 at 12, which is probably here or here. It is here, 20 volts, yeah? So the controller acknowledges the voltage and then starts to open these two MOSFETs. We have 20 volts here. Then we have the gate voltage, the 1.8 volts I've talked about before. So this P-channel MOSFET can open and let the current flow from here to the second MOSFET, and here it is the same. We have 1.8 volts and the voltage finally reaches this current sense resistor, 20 volts. And here on the other side of the PD controller we have the other two MOSFETs related to the other USB-C port. And on the other side, these two MOSFETs here the voltage cannot pass this first MOSFET. It will stop here with around 20 volts, gate voltage also around 19.5, and here just no voltage to protect the port. So yeah, the 20 volts have passed the circuit, and now the work of the PD controller is more or less over, and the charging controller can start with its work. And the confusion may start because we have two USB-C ports here, so almost each component here is doubled. So we have two MOSFETs here, we have two MOSFETs here. It's the same with this over voltage protection switch. One is here, the one related to the other USB-C port is here. Same with the port protector. We have one port protector here, which is related to this USB-C port, and the port protector related to our USB-C port is on the other side of the board. So yeah, almost everything is doubled up because each port has to go through the same sequence before it reaches the charging controller. And now finally we have reached something almost everyone has already noticed on a modern device with PD circuit, which is this circuit here, consisting of one MOSFET on one side, a coil in the middle, and another MOSFET on the other side. This is our actual buck boost converter. Here the work of the charging controller starts. We have our 20 volts here at drain 1 of the first dual MOSFET, and yeah, like before, please correct me if I'm telling something wrong here, but I understand it like that. The voltage will convert it to the 10 volts at the output here. 10 volts. This is our main power rail, 10 volts. And this is from our charger. So the power will be converted either with this MOSFET only or with the help of the second dual MOSFET. I don't know exactly, sorry for that. However, it will be converted from 20 volts to 10 volts, which is our main power rail in the end, and for some reason, I can't tell why, I almost never measure any voltage at this coil. You see, no voltage here. So you might think you are dealing with a dead motherboard here, but no. It is absolutely normal to measure no voltage here. I can't tell why it is like that. Maybe someone of you can. If so, please tell me. Please leave a comment and tell me, why don't we have any voltage here? I can't tell. So yeah, this is our buck boost converter. But well, we have only experienced the buck version of our converter, because the conversion to a lower voltage. So how does the boost converter work? I can give you a small example. We already know the main power rail is supposed to be 10 volts, right? So what do you think, what will happen when I come with the phone charger, which is supposed to be 5 volts? Should we try? We try it. Let's plug the phone charger. So here, the USB-C meter says 5 volts. So now we have plugged in a 5 volts charger and we have a blinking power button. So let's do a few checks again. So what do you think? Will the 5 volts pass the PD controller circuit? Let's see. We have 5 volts at the drain 1 of the first MOSFET. And now the magic happens. This is why this is called a buck boost converter. When I measure the output now, you won't believe. Maybe you will. I have 10 volts at the output from a 5 volts phone charger. Well, the power which is delivered here is of course not enough to power on the device. If I press the power button, nothing will happen. Let's press it. So simply nothing happens, because the phone charger is just rated 2 low amps. So nothing can happen. But this is why this is called a buck boost converter. It can actually work with 5 volts and step this 5 volts up to 10 volts. Because of this great introduction of a buck boost converter. I understood it like that. The voltage which comes to this coil will be stored for a very, very short while in this coil. And because of the perfect timing, the MOSFET's opening and closing, the next time this MOSFET will open, it can take the voltage which is stored here and boost the voltage to a higher value. Well, there are also some capacitors into the game, but I understand it like this, that the magic happens when the voltage is stored inside of the coil. However, I have never measured any voltage in this coil. Also when I measure between the pads, there's also nothing to measure, nothing to ground. Well, a little bit, 120 millivolts, but you see it is almost nothing. Yeah? Okay. So, yeah, this is a basic guide how these things with USB-C are working right now. And this is a very simple device. This is still a very simple device. We don't have a DC inject here. We don't have some kind of port replicator here, where the board is supposed to have an additional selector circuit, which can also be the case. Well, and when it can happen that that a schematics of a charging circuit from one page abnormal raises to like 6 pages of DaVinci in circuit. It is a nightmare, yes, but yeah, if you understand how this all works, you can do it, you can figure it. Okay? So, if you have any questions, please leave it in the comments. If you think I've told something wrong here and you can explain it better, please feel free to do so. I'm always happy to learn something. And yeah, otherwise, as always, thank you for watching and see you the next time.